Okay, in this video, we are going to look at our next chapter, which is forces. All right, so we've already been talking about forces, even though we haven't necessarily used that word. We know that acceleration is caused by our push or pull, right? When we push or pull on something, that's what makes it change its acceleration or to have an acceleration. And now we're going to go a step farther with that, right? Forces are defined as any push or pull. So it's really forces that cause things to accelerate. Um, Other thing we know is forces are vectors. We care about the direction, right? And that's, again, we've already been kind of working on that, right? The acceleration has a certain direction based on the direction of the push or pull. We do have a new unit. The units are newtons. And really, newtons are invented because people are tired of writing 1 kilogram meter per second squared. So this is our base units, 1 kilogram meter per second squared. But instead of having to write that all the time, because we're going to be doing lots of things with newtons throughout the rest of the year, then we can just change that into a newton, and which is represented by a capital N. So there's the general part of forces, right? We do need to understand that it's vectors, it has direction, and it has a new unit. Along with this are Newton's laws, right? This whole section is based on Newton's laws. And Newton's laws govern, the problems that we're going to be dealing with, but really Newton's laws go a lot farther, and they really govern how everything moves or doesn't move, right, in the world. So when Newton made these laws, he really was talking about very specific situations. He was really talking about planetary motion. Why does the moon orbit around us? Why do we orbit around the sun? He was trying to explain how planets move. But it turns out after he, gave these laws and he used these laws to explain things, people realized that these explain how everything moves. And really, it's the basis of engineering. It's the basis of a lot of major fields, just these three statements. The first statement being an object in motion tends to stay in motion in a straight line. An object at rest tends to stay at rest. Changes only occur when there's an outside force. So there's a lot to unpack there, right? The first thing we want to say is, right, if I just look at these two sentences, I can write these in a much more succinct way. I could write it with just using a lot less words. An object in motion tends to stay in motion in a straight line. An object at rest tends to stay at rest. So what is he describing there? He's describing situations where velocity is constant, right? That's what he's really saying, right? Objects tend to have a constant velocity. If they're moving, they tend to keep moving in a straight line. If they're not moving, they tend to stay not moving, right? Or we could say it a different way if we understand what acceleration, we could say acceleration is zero, right? Both of these statements are just fine. And that's really what we're describing in those first two sentences. We're describing situations where the velocity is constant and acceleration is zero. So we could take out those two sentences and put either of those in its place. It would be just as correct. But then the next thing is something new, and that's that changes occur only when there is an outside force. And this becomes important because it's saying something that we need to really understand. It takes an outside force to make something change its motion. And so technically, right, you can't do it to yourself. A car doesn't make itself go forward. Something outside the car makes that happen. When you're walking down the hallway, it's something outside of you that makes you actually speed up going down the hallway or stop or turn or any of these things. It takes a force outside of you, which is different than what most people think when they look at this, right? So we always have to understand that, right? Things don't move unless something outside of them is applying a force. So that's part of what we have to look at, right? But there is always some type of outside force. Newton's second law is really the one we're going to focus on a lot because Newton's second law is the equation, right? The first one's more of a statement, and then the second one is an equation. So the sum of the forces equals mass times acceleration. We tend to write it like this. This stands for the sum of the forces equals mass times acceleration, right? So this is an equation that relates the forces and determines how something's going to move. I'm going to back up one slide, right? This is just saying, hey, if we apply an outside force, we expect to see something accelerate. And this is a fairly unprovable statement, right? Because we can't go out there and find an object that has no outside forces on it. They simply don't exist. We can't go find one, right? Um, Everything that's on the planet has outside forces. It has at least gravity on it, and normally it has gravity and other forces, and we can't take all those away. So we can't find anything that we could actually see that has no outside forces. Um, and even if we went into outer space, say, well, things in outer space have no outside forces. No, the sun and the planets are still pulling on those things too, right? So they're not moving in straight lines, constantly. So this is an unprovable statement. We can't really do anything to test this. We're just kind of buying it. And we have to do all three laws, to be honest with you, before we could buy everything. But but this is something we can't really use. Newton's second law is something useful. Now it's saying, okay, if you buy into the first law, well, then this is how we deal with how much acceleration is caused by different forces. Um, and that's the sum of the force equals mass times acceleration. Now, understand these are two totally different things. This left side, this is the sum of the forces. And what do I mean by the sum of the forces? Well, forces are vectors. So this is where we take all the forces and we add them up. And that happens to be equal to the mass of the object times its acceleration. So we could have a whole bunch of forces on something and it has absolutely no acceleration. That's a possibility because all the forces add up to zero, right? For example, you sitting in a chair right now, gravity's pulling down, the chair is pushing up. Those two forces cancel each other out. They just basically add up to zero. One's positive because it's up, one's negative because it's down. They're both the same amounts. They add up to zero. So this is something we can look at, right? We could apply this to situations all around. We can apply this to many real world situations and just analyze the forces and see how they add up. And if they add up to some number that's not zero, the object's going to accelerate. If they add up to zero, which happens a lot of times, pretty much if you look around where you are, there's probably hundreds of things where the forces all add up to zero, and it's not accelerating. It's not going anywhere, and its velocity is not changing, so on and so forth. So this is the one that we tend to focus on because this has real world applications, and this is absolutely a provable statement. Newton's third law, when an object applies a force on a second object, the second object applies an equal force back. This becomes important. We're going to look at it in examples, but this also goes back to Newton's first law. Changes only occur when there's an outside force, right? It's really Newton's third law that helps explain real world situations, right? If I'm walking down the hallway and I'm speeding up, right? So I'm accelerating. And if I'm accelerating down the hallway and then people ask, well, what's the force? Then we'd say, well, you're doing it to yourself. Well, no, it can't be me, right? It has to be something outside of me. So really what happens is if I'm going to move, if I'm going to propel myself, it's not that simple. But what am I going to do? I'm going to push against the ground. I'm going to push back against the ground, and the ground pushes me forward. So the ground is the outside force that makes me move. And if we think about it, right, if I push real hard against the ground, I should move pretty fast. If I push real hard against the ground, but I was on ice, I'm not going to move very fast, right? If I push really hard on the ground and I was in really loose sand, I'm not going to move really fast, right? So the ground absolutely makes a difference to how fast I go because some surfaces, if I push hard against, I'm not going to do anything. I'm just going to slide, right? So I'm not really applying a force at all. I'm just going to slide over it. So, there are outside forces that make things move, and that's what it means when we look at more complicated situations, right? In order to make one thing move, it has to push against something else, and that second thing makes it move, right? When a car goes, right, the wheels spin. What do? They push backwards against the road, and the road pushes them forward, right? So this is how it works, and this is how it ties in with this other situation if it takes outside forces. If you have nothing to push against, right? If I'm floating in space, and I could swing my legs all I want, but it's never going to make me go forward because I don't have the ground to push against. Therefore, the ground doesn't push me forward. So there are Newton's three laws. We'll absolutely be using these. Most of the time, we're going to be using the second law, but the third law definitely comes into play, right? There's definitely situations that we have to make diagrams for and analyze and say, okay, what is pushing and pulling on this object? But in order to incorporate these laws, we have to look at the different types of forces. And there's so many types of forces out there, we're not going to be able to look at them all. But the first one that we're going to look at is gravity. Gravitational force is the attraction between any two objects with mass. which means every object you could see is pulling on you right now. And you're pulling on it, right? If there's two books in your room, those two books are pulling on each other. They're each pulling on you. You're pulling on them, right? The pencil, a pen, whatever it is, right? If it has mass, it pulls on everything else. Now, why does this happen? How does this happen? We honestly don't know, right? There's a lot of theories out there. You're welcome to go look at them all. There's a lot of it, right? And they're very complicated, many of them. So are they right? I'm not really sure, right? We know what gravitational force is. We can do tons of calculations about gravitational force. We could plot, manned and unmanned spacecraft through space by calculating the gravitational forces, and they're extremely accurate, right? NASA and other countries do a very good job of using the known calculations for gravity and navigating with this knowledge. So we're really good at understanding, the laws of gravity and how to incorporate those laws and how to do calculations based on this. Why is there gravity? I don't think anyone knows yet, right? What makes objects attracted to each other? We don't know, right? And that's definitely part of it. And that's one of the things that people have been working on for years. When I say years, I'm talking about thousands and thousands of years at this point. Right? The first scientific studies ever recorded were about why do things fall, right? And that was, the Greeks did it in, I don't know what year BC, the Chinese did it maybe even earlier than that. And here we are, past year 2000, and we still don't have that question answered, right? But this is the general equation, right? The force of gravity equals G, which is a constant, times the mass of the first object, times the mass of the second object, over r squared. Now, we're not going to spend a lot of time using this equation because if you think about it, how hard is, like, if you're sitting in a room right now and there's a book, how hard is that book pulling on you right now? Well, it's too small for you to even notice, right? And everything you could see in that room is pulling on you. Can you feel any of those pulls? Absolutely not. Do you get affected by any of those pulls? Absolutely not, right? So one of the things we know is the gravitational force is the weak force. That's what they call it. And this equation that I put up is useful in certain situations, right? We can calculate how hard your pencil is pulling on you. But the thing is, it's not really a useful number because it's just going to be incredibly small. So we tend to use this the way Newton intended, which is to talk about planetary motion, right? We have two planets and how far apart they are. We can figure out how hard they're pulling at each other because it is the gravitational forces that make things curve around the sun and the moon curve around us and so on and so forth. But most everyday things don't apply a large force. And if we use this calculation, we're just going to get tiny, tiny answers, which is proven, hey, this stuff is small. Now, with that said, there is one object that pulls on us hard enough that we do notice it. And that's the pull of the earth, right? So the pull of the earth is one of the forces that we care about, right? Our weight, and this will be a next slide, our weight is determined by the pull of the earth. So if we think about this and I use this equation, I say, okay, how hard is the earth pulling on you? Well, what we have is we have a gravitational constant. We have this gravitational constant of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So G is just a constant. That's a number we use whenever we're calculating gravitational forces, right? And there are some interesting, if you're into history and scientific history, there are some interesting experiments that happened a long time ago to try and get this value. And there was many scientists that were trying to get this value, and it's interesting to see the contraptions they came up with and the experiments that they came up with to try and get this number because it's so tiny, right? Any small errors in your lab are going to make this number, unattainable. So it's actually pretty interesting. But either way, this is the constant. And then mass 1 is the first object, mass 2 is the second object, and r is the distance they're apart, and we have to square that distance. So if we're looking at the pull of the earth, well, g is just a set number. It doesn't matter what we're looking at. It's just a set number. But mass 1, well, mass 1 would be the mass of the earth. The radius, well, what would be the radius? What would be the distance from you on the earth and the earth? Well, so we have the earth, and this is nowhere near to scale. Here we have you on the earth. And what's the distance? Well, some part of the earth is real close to you. Some of it's real far away. Some of it's over to the left. Some of it's over to the right, right? There's a lot of earth out there, and it's all very there's many distances to many different places on the earth. So when we're looking at the radius, we're really looking at the average distance for all the different places, or we're looking where the center of mass is for the earth, and that's right in the middle. And this is lots of times why Newton used r in this equation. So the distance that will work for us is the distance from the center of the Earth to where you are, which is basically the radius of the Earth because you're on the outside of this ball, right? So this is where it comes from. Where r stands for distance, the distance between the two objects, we tend to use r as the symbol, or we always write this equation with r as the symbol, because when we use this equation, we're talking about something that's a circle the vast majority of the time. Um, right now, we're using the Earth, and the radius is the distance to the center. So that's what r. If we're talking about us going around the sun, well, we make a circular path where r is the radius of that circle, right? So it tends to work out that way, which is why we don't use our normal symbol for distance, x, because we tend to be talking about a radius. So if we're talking about how hard is the Earth pulling on you, then we need the radius of the Earth. So I'm writing it this way just to point out that we have an equation that calculates gravity in all cases, but we don't care about the pull of 99.9% of the things because they're just too tiny. When we use this calculation, it would just be too small to get. But if we want to care about the one thing that does pull hard on us, that would be the pull of the Earth. And if I'm dealing with the pull of the Earth on anything, well, all of this doesn't really change. If I have a rock and it weighs 5 kilograms, well, it's sitting on the edge of the Earth, which has a distance that's equal to the radius of the Earth. The mass of the Earth doesn't change. G doesn't change. If I put a building on the Earth and I want to know the gravitational pull of that building, well, it's still the same thing. It's still the mass of the Earth. It's still the radius of the Earth. It's still G, right? So the vast majority of this equation doesn't change when we're looking at the pull of anything due to the pull of the Earth. So really, 3 of the 4 things don't change when we use this calculation in everyday life. So we're going to shorten this calculation. We're going to shorten this equation, and we're going to take all of this stuff, and we're going to just set it equal to one value. So when we know that one value, we just multiply it by the second object, and we know how hard the Earth is pulling. So we don't have to do all these calculations anymore. Okay, so a quick Google search tells me that the mass of the Earth is 5.97 times 10 to the 24 kilograms, and the radius is 6,371 kilometers, which means we have to convert that to meters. So that's going to be 6.37 times 10 to the 6th meters. All right, so let's do some unit analysis on this. I know my G, I know my mass of the Earth, I know my radius. So using this equation, I know so many things. Even if I don't know what object I care about, even if I don't know which object I want to calculate for, I still know all this stuff. So I'm just going to look at all this stuff. 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And we're going to multiply that by the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. And then we're going to divide by the radius squared. Right, so we plug these in, and we have 6.37 times 10 to the 6 meters, and we're doing that twice. 6.37 times 10 to the 6 meters. And then I'm not including this. I'm just doing the stuff that I circled. So meters cancel out. I have 2 on top, 2 on bottom. This kilogram cancels out one of these. So I have an answer that's newtons per kilogram. And when I do the math out, it gives me a number that, that I already know about, 9.8. So this works out to be 9.8 newtons per kilogram. If I carried out my unit analysis farther, I would get 9.8 meters per second squared. This is where this number came from, right? So G is what I get when I deal with the mass of the Earth, the radius of the Earth, is gravitational constant. I get G. And I can look at this 2 ways, right? If I have a 1 kilogram object, I'm going to feel a force of 9.8 newtons on it. If I have a 2 kilogram object, I'm going to feel a force of 19.6 newtons on it, right? So if I keep it in these units, then I can just directly change from kilograms to newtons. It's kind of the ratio, if you will. But I'll also use it in meters per second squared because we're going to see, forces cause acceleration. We also know in free fall, we said in free fall, objects accelerate at 9.8 meters per second squared. Well, here's the proof that they accelerate at 9.8 meters per second squared. This is the acceleration that we cause. And we know, we already said the sum of the forces equals mass times acceleration. So if we're in a situation where the only force is gravity. Well, the force of gravity equals mass times acceleration. Well, what's acceleration? 9.8 meters per second squared. So we have a new equation then for gravity. The force of gravity, if I want to calculate the gravitational force on an object, we take its mass, the mass of the object, and we multiply it by g. And we know the direction for the force of gravity. It's down. So there is my new simplified equation for the force of gravity based on the full equation for the force of gravity. Now, with that said, we have some different terms that we need to understand. Number one is gravitational force. That's what we just defined. It is the attraction between objects with mass. It is equal to g times m1, m2 over r squared. And we can calculate, and we could use this gravitational force for anything, anywhere. Different than that is weight, and I'm going to jump all the way down. Weight is the force of gravity due to the Earth for an object on the Earth. And it's a long thing just to say, this is the, when we're dealing with weight, we're dealing with how hard is the Earth pulling on things that are on the Earth. So for an object on the Earth. And weight, lots of times, is really what we care about, right? I mean, it's still a gravitational force, but it's a very specific gravitational force. But it's a gravitational force that matters to us, because if we're dealing with calculations in engineering or just in physics, most of the time we're dealing with something that's on the Earth. So the force of gravity in that case equals mg. Mass is something completely different. Mass is the measure of inertia. So what's inertia? Inertia is the tendency to stay in a state of motion. So if something's moving and it has a lot of inertia, it's going to be hard to stop it from moving. It's going to be hard to make it turn. Also, if it's not moving, it's going to be hard to get it to move, right? So inertia is the measure of how hard it is to get something to change what it's doing, right, or to stay what it's doing. So inertia is that. Objects tend to want to stay, and if they have a lot of inertia, it's going to be hard for you to make them to change. Inertia is mass. Mass is the measure of inertia. Which is different than force, right? Inertia is just how willing is it to change, not how much force did you apply to it at all. And how do we measure mass? Well, we measure mass in kilograms. So kilograms has lots of meanings in lots of classes. Chemistry certainly defines it differently, but it is the measure of inertia. And that hopefully makes sense, right? If you want to stop something, well, what's the key thing that determines if it's easy or hard to stop, right? How massive it is. Also how fast it's going. But if you just want to change it by a certain amount, then how massive it is matters. So mass is different than weight, right? And we want to keep that in mind. When we say something weighs 3 kilograms, we're already wrong. It doesn't weigh 3 kilograms. It has a mass of 3 kilograms. What it weighs is 3 times 9.8, right? Which is what, 29.67? Whatever it is. All right. Our second type of force is the normal force. The normal force is the force that stops an object from falling through the surface. So the normal force is, lots of times what holds things up. And there's no equation for normal force. If I had a block and the Earth was pulling with a force of 5 newtons, that's my force of gravity, then what would my normal force be so it doesn't fall through? Well, my normal force would be 5 newtons. It's always just enough to cancel things out so objects don't fall through the surface. And they don't always have to be up. They're not always canceling out gravity. I could have a normal force if I push against the wall, right? If something's leaning against, the wall, then the wall is pushing out to stop it from falling through the wall. But that's not equal to gravity. That's just equal to whatever force is pushing against it. So the normal force we'll have to look at in examples, because the normal force can vary on different situations. With this block has a force of gravity of 5 newtons. So the normal force is 5 newtons up. But if I put a second block on it, and that second block has a weight of 3 newtons, well, now the normal force is 8 newtons, because that's to cancel out both of those. If I push down on this block and I push down with a force of 10 newtons, well, the normal force is now 18 newtons, because it has to cancel out the 3 newtons of this weight, the 5 newtons of this weight, and the 10 newtons that I'm pushing down. right? And if it doesn't cancel them all out, well, then that means I'm strong enough to push it through the ground. So no, the normal forces, we have to understand the situation and see how much force is there that the normal force has to cancel out so it doesn't go through whatever surface it is we're talking about. So these are the forces that we're going to be focused on in the examples in the other videos. And we are going to talk about one more in the next video, which is frictional force.